Today I'm going to introduce some of my recent work on the stabilized Galerkin Meshfree formulation for advection dominated flows, and how I use the concept of Meshfree to integrate into the machine learning formulations to enhance its learning ability. So before I proceed, I just want to dive into the main thing. I just want to briefly introduce, if you don't know me, I work on Meshfree methods, computational mechanics for extreme event problems, as shown here. These are my recent demo, recent simulation results. And also recently using the neural network enhancement to speed up the finite element and do homogenization for multi-scale modeling, and also including using a neural network machine learning to enhance Meshfree method, as shown in this speech. So you can see that I mostly work on Lagrangian mechanics, Lagrangian solid mechanics, but why I choose Galerkin advection as my research topic in here. And the reason is I want to challenge one concept is that you mostly see Meshfree methods modeling fluid flow like this, because in Lagrangian mechanics make use of its Meshfree property, but it doesn't mean that you cannot use it for Galerkin type of simulation that involve advection. And advection is a very important phenomenon for shock wave, for turbulence. So I want to show that Meshfree can also do that, and because most of you may use just finite volume, finite element, IGA to do that. But I will show you that I can improve the performance of the Meshfree method in Galerkin mechanics to modeling advection, and also to show that I can use that concept to develop new machine learning methods inspired by Meshfree. So I'll use the standard advection diffusion equation to demonstrate the idea, although the formulation can be extended to Navier-Stokes equation, which I already done. This is a strong form of the problem where LU is the flux divergence operator that including the advection and diffusion flux. And by integration, by parts standard procedure, you get the Galerkin weak form as shown here. But it is, I'll say, notorious or very well known that the traditional problem of Galerkin formulation suffers from a numerical instability, that you will see strong oscillation and numerical artifact near the boundary, especially when you face a high Peclet number, meaning the advection is really, really strong. So, there's a well-known method by, the big name Tom Hughes, the variation multi-scale methods. You can use that to stabilize the results, and also for boundary condition, you can use weakly imposed boundary condition by Yuri Vasilevs and Tom Hughes again to solve the problem. The idea is they can introduce the stringline upwinding SUPG, well-known SUPG formulation, and also niche-like formulation to impose compatibility, regularization on the inflow, outflow, and also introduce additional coercivity to enhance the solution stability. And here we choose Meshfree reproducing kernel approximation due to the advantage that Persian have mentioned before, the control of local smoothness, the order of completeness, etc. And because of each Meshfree method, we usually adopt with nodal quadrature. But the methodology that I show next following on does not restrict to Meshfree. You can do that for IGA, for FEM as well, as long as you are using low order quadrature. And here I'll show two figures about using the above schemes that on simple 1D advection diffusion equation. This will be the convergence plot you will obtain. The colorful scheme curves are from nodal integration. You will get only rate of 1, although you're using linear approximation. And unless you are using high order Gaussian integration, then you can get better convergence, desired convergence rate, but that will be cumbersome, of course. And the other issue will be the instability, that under high Peclet number, like this one is the boundary layer problem in 1D, you'll see the nodal integration shows these unstable modes. Right? You don't see that modes really strong in diffusion case, like Stokes problem or Poisson equation. But when you have advection diffusion, you have high Peclet number, you see this strong oscillation. So in order to address that, I basically borrow this idea from JS earlier work. One is called variational consistent integration. The other is called NSNI, which is a gradient-based stabilization. So the first one, the accuracy is due to the inability of approximation, especially for the test function, to reproduce Galerkin exactness in the variational equation of advection term, especially for advection term. So the idea here is I assume my solution, the trial function is a linear field and with specific test function, and substitute into the weak form of the advection equation. For the diffusion part, if you check the diffusion part, you'll find out that the test function needs to satisfy actually the divergence theory. Okay, so that will cause, that is actually called the linear constraint in the BC paper. But for the advection part, the tricky is you will find out that it actually requires the so-called quadratic condition in the VCI paper. So that means we need to have an extended condition to impose for the test function. Still, we can use so that the main point here is that even for linear approximation, you need quadratic correction for the test function. And you can use the assumed gradient approach by imposing this residual, the error residual shown here, back into the test function to correct the error. Then you can recover the optimal convergence. The second enhancement you can do is by using the gradient type stabilization by introducing the high order Taylor expansion on the test function and trial function. And the key here, what I did here is to introduce that to the VMS term, the variable scale term, instead of the advection term, because first you will violate the BC2 condition, this one, because if you simply do straightforward Taylor expansion. The second thing is advection term is the non-self-adjoint operator, and the high order terms put on it to it, maybe you can imagine it's more like enhanced integration that will actually show a little bit more oscillation from the numerical observation or in our inner testing. So we'll actually do that for the VMS term to obtain more stabilization. And for the detail, you can check my paper in recent CMME paper recently published. So here are the results you can show here that you can see no matter for the nodal integration and the Gaussian integration, you can say I show the rate of convergence of 2 for regular discretization, regular and irregular discretization. And also, of course, nodal integration shows much better computation efficiency rather than the Gaussian integration. You can use this one for IGA, your finite volume method as well to enhance that. And also it can enhance the transient problem, of course. You can see those spurious waves are gone for these cone advection, cone rotating problem. So that's from Meshfree. So I have shown some method to correct the Meshfree formulation for advection. So I want to dive into the machine learning. Okay, so machine learning is I have to mention this famous work by Professor Kardianakis from Brown, the famous physics in full neural networks. So by formulating these kind of least square like energy functional, and to minimize it through the penalty formulation to impose this is a multitask problem, so we have to introduce penalty parameter to impose the constraint. We can solve the problem in a strong form sense. And since physics in full network, it's actually more like a Meshfree method. You don't need the discretization. All you need to do is to choose different sampling points and formulate the physical laws in the least square type by penalty method and optimize it. You can use TensorFlow, you can use PyTorch. And but you will find the problem is that the penalty parameter will be tricky in the advection diffusion problem, because if you choose large penalty parameter, you get yield condition. If you choose too low, you cannot impose it. And also, we found out that the boundary condition, the inflow and outflow, actually you need different regularization. That will become the issue in modeling. If you're really in modeling the fluid problem, you'll find out that not all the schemes that really converge. So to enhance it, I actually revisit the two main famous schemes by Hughes and by Hughes for the VMS and WBC, the weakly imposed boundary condition. The idea is, since although I use least square type functional, I can design a least square functional that is similar, for example, to the weakly imposed boundary condition to impose coercivity, for example, and to impose the different regularization on the inflow and outflow boundary. And actually, for the formulation shown here, if you take variation, it will degenerate to the WBC formulation. Okay, so this is for the boundary. And for the non-convergent or learning ability issue, what I did here is, although I use least square, I can still do multi-scale decomposition. You can do something like what Professor JS did, to use RK for the core scale, to use neural network for the fine scale that derive the scheme. But here I didn't do that. I just used neural network for everything. So you can substitute into the least square formulation and then do variation to derive the fine scale solution, what it looks like. And eventually this will be the final equation. Right? You can see that this one actually comes from the least square loss of the momentum balance equation. And this actually gives you what? Additional term. That looks like this, where LUH minus S is the strong form loss, and you take advection operator on it. So this is similar actually to the so-called soft law training, and I think it's Sun Wei-Xin's paper, recent paper, in the crystal plasticity to enhance the learning ability, or more recent paper by Professor Kardianakis for so-called gradient PINN adding gradient term. But for their methods, they don't have specific definition on these parameter, regularization parameter C. But here, because of this procedure, I can actually derive the form of C. Okay, and actually I only need C in the simulation solution. C is 10 to the power of -4. That's enough for my purpose to model the problem. So show this one, static using Monte Carlo integration. It's one kind of nodal integration. The gray and light blue curve are by conventional penalty methods, and neural network strong for enforcement method. You can see that solution even diverge or not satisfy that good. And the blue and red curve are the proposed scheme. You can see that with VMS you get better learning ability. And also this is the famous advection skew problem. You will see that on the diffusion limit, even penalty method, if I didn't choose penalty, I already regularized it, it does not satisfy the boundary condition very well. The proposed scheme, two schemes are match the FEN solution. FEN I use 100 by 100. This one I only use 10 by 10 neural network sampling points. You can see the accuracy is amazing. Also, here you can see that at advection limit, you will see penalty method directly diverge. And my solution, WVC and WVC plus VMS, is very close to FEN. WVC shows a little bit overshoot and undershoot behavior that VMS can cure that, but from 2D figure, we can see I cannot show that. And this is my recent progress to do shock modeling for Berger's equation. You can see that I apply the method to the Berger's equation, nonlinear transient. Probably you can see that all the shock wave refraction and shock wave and this shock nodes are captured. So I think due to the time issue, maybe I'll just quickly conclude. So I provide Meshfree correction to model advection, and I show that we can, even for people, I usually used to work on conventional Meshfree numerical methods, but now even machine learning is a popular field. I'm not afraid of that. Some of the method, the idea that from the numerical method, those mathematicians, when they develop the method, that can actually use in machine learning. That's what I'm trying to say. And we can get better convergence, robust simulation results, and outstanding efficiency. So with that, I will conclude my talk. Thank you.
期待更多年轻的朋友加入学会。那学生是特别便宜哈，现在加入有优待，所以欢迎学生在外面加入。那如果你没有钱付钱，找你的指导教授。那我们再一次谢谢这些人哈，这个非常精彩的演讲。还有我们4位讲者哈，谢谢。那我们今天活动就到这边，谢谢大家今天的参与，谢谢。